I'm very pleased to introduce Annika Peter this morning. Creative Mornings, as everyone on this call knows, tends to draw artists and poets and designers, creatives, we sometimes call them. Today, we wanted to bring a scientist in conversation with our community of creatives. Annika is an associate professor at The Ohio State University, where she works at the interface between particle physics and astronomy to answer the question, what is dark matter? We invited her today to share with us how she makes the invisible visible. Speaking this morning on the theme, invisible, please join me in welcoming Annika Peter.
Thank you for that. Let me see if I can share my slides, which, PowerPoint is the language of physics for, for communicating with audiences. Okay. All right. So I hope one of my goals for today is to convince you that actually physics is an incredibly creative endeavor too. So sometimes people think about science as being sort of dry and boring, but my goal for today is to convince you that that is absolutely not the case. All right, so my talk today is focused around the question, how do you see the invisible? So this image here that I'm showing you on the screen is a small galaxy. So as we're going to talk about, a galaxy is a collection of stars and gas and dust. And this little galaxy here is a companion of our own galaxy, the Milky Way. This little galaxy called Fornax is orbiting around our galaxy. And what I'm going to show you is that the visible part of Fornax is just the tip of the iceberg, that if we were able to see the invisible, we would see a massive structure around it. Okay, so let's move on to talk more about what a galaxy is. This is a different type of galaxy. So one thing that is amazing about our cosmos is that objects that we give the same name can actually look very different from each other. So this galaxy that I showed you before, Fornax, is a relatively small galaxy, a type of galaxy that we call a dwarf galaxy. And it's sort of round and puffy. A galaxy like the Milky Way, or this galaxy here, this is a simulation. So not an observation, but something that one of my OSU colleagues, Sam Benincasa, simulated or modeled on a computer. This type of galaxy is called a spiral galaxy. Okay, and so we see different types of things in here. And each of the colors that we see here traces a different part of the galaxy. So one thing you'll see is a lot of blue regions here. Those are places where stars are actively forming. This dark spider web here, this is what we call dust. So dust is basically just complex molecules. They do a really good job of absorbing optical light. And that's why these dust lanes look dark or not very luminous. It's because those are parts of the galaxy that absorb light. They actually re-emit light, as I'm going to show you in a little bit, in different wavelengths. So if we're able to put, goggles on to see a different type of light, then we would see the dust glow and the rest of the galaxy not glow. Okay, let's go into that maybe a little more. So this is a beautiful rendering of a fake galaxy made on a computer, but meant to look like this real galaxy. So this is a simulated galaxy. Let me show you what real galaxies in our universe look like if we look at them with different types of light. Okay, so this is a plot from one of my other OSU colleagues, Adam Leroy. And what we're seeing here are 4 nearby galaxies, all spiral galaxies. And each color of light here represents a different type of light that traces a different component of the galaxy. So the old stars glow in red. So these we observe in infrared wavelengths. So if you had an infrared camera, like, night vision cameras, what we would see is the part of the galaxy that here is indicated in red, and that indicates old stars. On the other hand, if we could see ultraviolet light, like some birds can, and we were looking at the sky, then what we would see is this pink and purple zone here. Okay, so if we are birds who could see ultraviolet light, then what we would be seeing is new stars, stars just being born. And then my colleague Adam, he works in radio wavelengths. So radio, sort of just like, the radio waves that we send and transmit on Earth to communicate, the news or music. Galaxies also glow in these radio wavelengths. And so radio, which is indicated in blue here, indicates where there's a lot of gas that may turn into stars. Okay, so zooming out, what I want to tell you, or what I'm showing with these images, is that when we're trying to learn about galaxies, these collections of stars, gas, and dust, the way we learn about the components of the galaxy is by looking at these different types of light, because the different types of light are emitted by different parts or different types of objects in that galaxy. Okay, so historically, this is how we've learned about not just galaxies, but like individual stars, even like planets now. We look for the light that those objects emit, and the different types of light tell us about different parts of those bodies. Okay. Oops. Okay, so what if there's something in the galaxy that does not emit light? How do we find out about that? So I just got through telling you that we use different types of light to trace different parts of a galaxy, but that presupposes that each component in a galaxy emits light. So what happens if there's something that doesn't emit light? How do we learn about that? So let's consider air. So air is transparent, at least at optical wavelengths, and optical wavelengths of light are what our human eyes are sensitive to. Now, if we were all in a room together, I would be able to see your faces in the room, even though there's a lot of air between you and me. Okay, and the reason why I can see you is because the air is transparent. So how do I know that air is there, that it's a real thing? My example of how we can figure out what air is, or rather that it's even there at all, is by considering the effect that air has on objects that we can see. So this is a GIF actually that I just found online thanks to Google. But this is an image of a GIF of a wind farm in the Mojave Desert. And what I can see is I can see the blades of the windmill, and I can see them move. And the reason I can see the blades of the windmill move is because sunlight bounces off the blades of the windmill, and then that light comes to my eyes so I can see it. All right, but I see these windmills turn. Why are they turning? It's because the air is moving in what we call a wind, and that wind pushes on the blades and causes them to rotate. Okay, so I can tell that air has to be there because of the effect it has, the physical effect it has, the effect that it moves things, the things that I can see. Okay, are you all with me so far? Because I'm going to do a hard pivot into something slightly more abstract. Okay, I can't actually see people, but but okay. All right, so that's air. Now let's consider the motion of galaxies. So galaxies aren't just static, like in this picture, but galaxies move. So this again is a video by my OSU colleague, Sam Benincasa. And so she's made a movie here of the outputs of her galaxy simulation as a function of time. And so you can see that the galaxy moves with time. Now it moves slow enough that on human timescales, we're not going to see this rotation happen. But we can measure how fast something moves in an instant of time, just sort of like, you know, speed guns on like a baseball field can tell you how fast a baseball is moving at an instant of time in time, or how fast a car is moving on the street. We can measure in an instant of time how fast each component of a galaxy moves. And so let's consider what happens if there's not much mass in a galaxy. Now, if a galaxy is not very massive, the components of that galaxy are going to move pretty slowly. Now, if you all were a bunch of physicists, I would be putting some equations up here because we use the language of math to express ideas in physics. So think about math as a language, and that's a language that's highly, you know, is the language, one of the languages we speak in physics. Okay, here I'm using a video to represent this idea. Okay, so if an object has less mass, then the components of that object are going to move slowly. But if a galaxy is massive, then the components of that galaxy move much more quickly. Oops. I'm still getting used to showing videos and talks and not have them restart so often. Okay, so where are we going with this? So actually, since the advent of radio astronomy in the 1950s, but really pushed hard starting in the 1960s by Vera Rubin and colleagues, people have been making measurements of how fast different components of galaxies move at that single snapshot in time. Okay, and the amazing discovery by Vera Rubin, her colleague Kent Ford, and many others is that the components of galaxies, like the gas, dust, and stars in here, are moving faster than we expect. What does that mean? Okay, so I'm going to drop a little bit of, so I talked about how math is one of the languages of physics. Another language of physics is graphical representations, like plots. Okay, so this is my one piece of like physics language that I want to leave you with today. So I'm going to explain what we're seeing here. So this is, these are two images that I took from a very important paper by Vera Rubin and her colleague Kent Ford from 1970, where they were looking at our twin galaxy, the Andromeda galaxy. So the Andromeda galaxy is a lot like the Milky Way and is really close. And in a few billion years, we're going to collide with the Andromeda galaxy and then form one big galaxy together. But that's far off. You don't need to worry about it. It's not going to happen on any sort of human time scale. This image on the right shows what the Andromeda galaxy looks like in optical wavelengths. Each one of these points on here is a point where there are young stars forming. And where those stars form, it creates a bubble of light that is of a different wavelength than the rest of the galaxy. Okay, so Rubin and Ford were able to make measurements basically of how these young star forming regions, how fast they're moving, because they emit light at a special wavelength that they can observe. And then they took all of these measurements of how fast each one of these young star areas was moving and turned it into this plot that we see on the left. So let me explain what we're seeing here. So the bottom, the horizontal axis represents distance from the center of the galaxy. So on the bottom, it's in what are called arc minutes. So that's basically a measure of angles. So that's how we see it and measured on the sky, is what's the angle between the center of the galaxy and that young star region. On the top is that scale in physical scale. So what's the distance measured, in this case, in a unit called a kiloparsec, which is about 3,000 light years. 1 kiloparsec is about 3,000 light years. Okay, so but zooming out, the horizontal axes are representations of distance from the center of the galaxy as projected onto the sky. And on the vertical axis, we have how fast these regions are moving with respect to the center of the Andromeda galaxy. Okay, so that's what each of these points is. And then they have fit these curves with the black and dashed lines. Now, if the only mass in this galaxy were the mass of what we see, this curve starting at about here would curve downward like this. Okay. But instead we see that these luminous young star forming regions, they're moving much faster than we expect, far out from where the main luminous light emitting matter of the galaxy lives. Okay, and so what that tells us is that there's a lot of invisible matter around a galaxy like Andromeda and others. So, so the galaxy that we see, the luminous stuff, is at the center of this giant structure of something that we call dark matter. And this structure of dark matter we call a halo. Okay, think of it just as a cloud of dark matter, a halo of dark matter around the visible part of the galaxy. This color map here is from a simulation by a German theoretical astrophysicist named Volker Springel. And the colors denote density, like how dense is the dark matter. And so the dark matter is densest at the center, where the luminous part of the galaxy is, and becomes less dense further out. But this cloud of dark matter, this halo of dark matter, extends almost 100 times farther out from the galaxy than the visible part. Okay, so the visible part of the galaxy is just the tip of this very large iceberg. Okay, and so what these observations tell us, in combination with many other astronomical observations, is that 96% of the universe is made of things that are unknown. So the way I like to represent our universe is like the cupcake. So everything that we know about and can see and emits light is like the sprinkles of the cupcake. And the invisible part of the universe, made of stuff that we don't know what it is 96%. That part is like the body of the cupcake and the frosting. Dark matter, like the structure that I showed you here that surrounds the galaxy, that's like the frosting of the cupcake. It keeps the galaxy together. It's actually very difficult to form galaxies without dark matter. So functionally, dark matter is like the frosting. It just holds the sprinkles together. Okay, so the goal of my work is to figure out what this dark matter is. What is this invisible matter? And the way I approach this, along with members of my research group in a much broader community of physics, is using galaxies. So these are a couple of pictures of actual galaxies. This is our friend Fornax. This, believe it or not, is another galaxy. The stars in that galaxy are highlighted in green circles here. Okay, so there's hardly anything to these galaxies, especially this one. But they're really embedded in these much larger dark matter structures. And so what the goal of my group is to use these galaxies of different sizes to trace the dark matter in our universe. And the reason that we want to do this is because different theories or models of what dark matter could be make different predictions for how many of those galaxies there are of different types. So these are graphical representations of the density of dark matter halos for different theories or hypotheses of what dark matter could be. And you can see that these all look different from each other. And so that's what that's our goal, is to measure where these dark matter structures are and characterize them, because that tells us something about what the nature of dark matter is. And the way we do it is by looking for teeny tiny galaxies of different sorts. So I'm showing some pictures of some of these are real galaxies. Like this is a galaxy that's being stretched apart and destroyed by another galaxy. This, believe it or not, is another galaxy over here. Over here, we're showing some galaxies that are real, and then we've put in fake galaxies in the images next to them, mostly so that we can test to make sure that we can reliably detect these galaxies of different types in our data and figure out how we can recover them from these observational data sets. Okay, so this is what my group does, or one of the actually many things that we do, is we look for these small galaxies of different sizes and with different properties that live in different parts of our nearby universe. Okay, but we still don't know what dark matter is. This matter that surrounds or is the nest in which baby galaxies hatch and grow. Okay, but we don't know what it is, but we're on our way to finding out. Okay, so this leaves me with a couple of thoughts to share with you in conclusion. Science is a process. It's not a collection of facts. So it's only been in the last 50 years or so that we've known that something like dark matter probably has to exist. And it's been only within the past 25 or 30 years that we've learned that another invisible component of the universe, dark energy, probably has to exist as well. So this is really new. What I like to tell people is that when my own grandparents were born, a lot of people, scientists, thought that our Milky Way was the only thing in our universe, the only big structure in our universe. We now know that the Milky Way is but one of an impossible number of galaxies in our universe. We know so much more now than we did 100 years ago. But there's still a lot of things that we don't know. And science is the process by which we figure out these things that we do not know. The other thing is that science is a collaborative process. So I feel like in the sort of public mind, when you talk about a scientist or specifically a physicist, people think of Albert Einstein or just the individuals who are just geniuses and they think of stuff. That's really not how science works. Science is a human activity. We work together to think about how we can learn about the mysteries of our universe. So what I'm showing you here is just a subset of my collaborators, just the ones who I started working with while we were all together at OSU. Okay, I have many collaborators all over the planet, and we work together to work on these questions and problems. The final thing, which I think is important, especially, we were talking about the Omicron variant before this, is that in science, we sit with uncertainty all the time. You know, if we knew everything there was to know about our universe, there would be nothing more to do. So I sit with the uncertainty of not knowing what dark matter is all the time. And that's, you know, I would really like to know what dark matter is. But even once we figure that out, there are going to be many other mysteries to wrestle with. And it just takes time to learn about new phenomena. So I just wanted to end with that. Science is a collaborative, creative human process where we have to sit with just not knowing things all the time. And that's both aggravating and an opportunity all in one. All right, so I think I will stop there. Thank you.
Marvelous. That's just simply marvelous, Annika. So, well, this is for everyone. As you have questions or observations, please write those in the chat. We'll try to get to those, as many of those as we can. So where to begin? So as I was hearing you talk about dark matter and some of the techniques that have been used to try to, well, to see it. I mean, that's what we're talking about, making something that's not visible, making something like that visible. To what degree do you, as a scientist, engage the imagination?
Oh, a lot. I mean, when you're trying to figure out something about something that's unknown or you can't see, you have to think about new ways to try to figure out how to learn about what you can't see. So so what I would say is that then that creativity manifests itself in different ways. So theoretical physicists or theoretical astrophysicists, they spend a lot of time dreaming of new ways you could new ways that the invisible can affect visible things. So every day there are new ideas about how dark matter might affect stars, the motions of stars, and then how we might make those measurements. Now, observers and experimentalists, they think about ways how we could actually do this. And that requires a lot of creativity because you've got to design new instruments and new facilities. And so what I would say is that these unknowns are organizing principles for people to express creativity. So for me, for example, I'll see a plot in a paper and I'll just meditate on that and think that will inspire me for a long time of, you know, why does this phenomenon look the way it is? You know, so what I would say is that the unknowns act as organizing principles for creative thought.
What's interesting, I was listening to your words there, dreaming, inspiration. I think a lot of people on this call, I think a lot of creatives would certainly understand that language, but I'm not certain we're accustomed to hearing it from scientists. This is fabulous. So Mary has asked, in user experience research, we talk about living in ambiguity. And she'd like to hear this connection in your work, living in ambiguity.
Yeah, so I mean, for me, you know, one of the things is that we don't know what dark matter is, but we have a lot of different hypotheses for what dark matter could be. So I see there's something in the chat about creative guesses. So the scientific word for creative guesses is hypothesis, which, thanks to my kids' previous love of the PBS show Dinosaur Train, the Dinosaur Train definition of a hypothesis is an idea you can test. Okay, and so for dark matter, we have a lot of ideas we can test. So a lot of different theories of what dark matter could be. And then based on what we think it could be, you can then think about how that dark matter manifests in the universe, how it affects things that we can see. Okay, so part of the ambiguity is that we don't know what dark matter is. But if we have hypotheses of what it could be, then we can make predictions for what we should be able to observe. And then we can test those predictions.
As I am, Brandy is impressed by the level of collaboration in the sciences. She asks, what facilitates such a high degree of interconnectedness in the scientific community?
Yeah, so the problems are so big, and the types of things that you have to do to test different hypotheses related to those problems are so big that we have to work together to do it. So my experimental colleagues who are trying to make dark matter in their laboratories, the big laboratory for that is the Large Hadron Collider in France and Switzerland. And so the collaborations that work on that are many thousands of people all over the globe. The detectors that they build, apart from just actually making the events happen in the lab itself, but the detectors that you have to make in order to analyze the interactions are the size, are bigger than my house, or about as big as my house. So, and it's like heavily instrumented. So it's not just like a big, house that's just sitting there, but it's got like, silicon trackers and all sorts of stuff in there. So that is a big effort. It takes a lot of people working together to make this big thing go. Another example is this James Webb Space Telescope that's supposed to launch, well, now on Christmas Eve, but things.
Who knows?
Yeah, but people have been working on that for decades, and it's astronomers, engineers, physicists, and then to keep those, also project managers, and then those rooms that you build equipment in have to be really clean. So you need to have people who can clean, keep clean rooms clean. There are all sorts of people who are involved in making that telescope fly.
Brandy, is what's drawing you to this sense of collaboration is that it's something that you don't see in other areas?
Yeah, I mean, I would definitely say that having like the degree to which you have to be willing to work with others to do the types of projects that Annika is discussing, I think is incredible. And so what I was thinking as she was talking is it the literally having a problem that is so difficult that it's impossible to do it alone? Is that what facilitates this? Because I don't see what she's talking about in education. I don't see what she's talking about in nonprofit or for-profit. I think it's incredible. It's really inspirational.
Yeah, the irony is that physicists are not, what I would say, people go into physics not because they love necessarily working with other people.
You're saying they're antisocial? Is that what you're saying, Annika? Or?
Right. I mean, I would say that physicists actually are pretty social, but they don't view themselves that way. It's different from in other spaces, I feel like, where, people skills are really valued and brought to the front. I think a lot of students are surprised, because of this notion in pop culture that, science is this like solitary endeavor. They get to college, or even more so to grad school, and then they realize that, physics is not just about slinging out problem sets by yourself or in a small study group, but it's where the value is in posing the right questions and being creative in solutions and working together with other people and communicating with those other people, communicating with the public. It's just a very different way of operating that is people so often go into. So it's really where the public perception is maybe actually pretty different from reality. I mean, I think we're seeing some of this change, though, in the context, again, of COVID. So when we talk about the vaccine developers, we're seeing, certainly we see some individuals in the media a lot, but what they will all tell you, I mean, I was just listening to This American Life about the development of the Moderna vaccine. It's a lot of people working together, and they will tell you that it's a lot of people working together. And that actually the reason they were able to get these vaccines out so fast is because they'd done a lot of work with MERS in particular in the years before, and it turned out that a lot of their work was transferable.
Mhm.
So I think that indicates, building knowledge as well as working together in teams. So we really build on each other to do new things.
So I had a question about collaboration as well, and I'm not aiming this for you specifically, but do scientists ever collaborate with, say, artists or poets or creatives?
Yeah. Yes. So I can give you a couple of examples, even just at OSU. So for a long time, we had a cosmologist named Paul Sutter here at OSU. He's now left OSU to become his own science communications enterprise in New York. But he collaborated with a ballet company to make a ballet about astronomy. The department chair in astronomy right now, David Weinberg, he very often collaborates with artists to make, artistic representations of cosmological surveys.
Sculptures. Does he make like sculptures?
Yeah.
I think I've seen some of these.
Yeah. So it does happen. It's maybe not as common as maybe it could be. Another thing that maybe is kind of an interesting way to think is that OSU has a planetarium. It's in the top floor of Smith Lab. You would never guess looking at Smith Lab that there's something that amazing inside of it. Amid all the yellow subway tile from the 1950s, there's this amazing planetarium. But we don't just use that for astronomy education, but like the School of Optometry uses it to represent the inside of an eyeball, for example. So there are a lot of, so that's still science, but you have to render things, and that is art as well, so there are all sorts of collaborations that are possible.
Well, I love those possibilities. I think that one of the takeaways, and I'm still sort of writing it and crafting this, but you had said that one of the ways that that physicists and astronomers have identified dark matter is that you can see non-light emitting things by considering their effect or impact on things that we can see.
Yes.
And I'm wondering if that isn't an analogy, certainly, for things that we could be seeing in our terrestrial world. I'm thinking, well, I'm thinking initially of things like the virus. In fact, it's long been said that maybe sort of the reluctance in some people have had to take mitigation efforts against the virus is that we can't see it, right? And so therefore it's somehow not real. But of course, what we can see all of its effects. But I was also thinking about this is an analogy for thinking about things like systemic racism.
Yeah.
Well, I can't see systemic racism, someone might say, but by golly, we sure can see its effects and impact on things that we can see, and people and relationships that we can see. So I'm wondering if there's not an analogy there for maybe our initial question: how do we make visible things that are invisible?
Yeah, I think those points are really important. I think part of what is so hard is that unless it's part of your lived experience, it can be really abstract. And because of evolutionary reasons, things that are abstract seem less salient or urgent than the things that we have firsthand experience with. So, that's true when people worry about flying somewhere and drive instead, where we know that driving is, you're much more likely to die driving than you are flying, right? But it's really, but driving is familiar, it's part of your lived experience, so, and I think one challenge is that we all have different lived experiences, right? And so you really have to talk to other people and be with them in some space to make their experience then also part of yours. And I think that is important to zooming out and then being able to see the invisible, is that you have to bring it somehow to be visible to you in your own life, because abstract things are just, for evolutionary reasons, really hard for people to wrap their minds around.
Cynthia, I think you should have the last word here in evoking Margaret Wheatley. Can you share this observation with the group?
Yeah, I've been thinking about it ever since the middle of the presentation, just that about the unseen. And I first read about this when I was into Peter Senge and reading Margaret Wheatley. And in one of her books, Something in the New Management Science, she did this description of the way the scientific method pays attention to the objects and not the fields, and how much we are missing.
Mm-hmm.
And I love getting to hear about physics and read about it, and really see this attention starting to turn toward the unseen and the field. And it excites me that there's this possibility for more curiosity of more people to turn toward what might really be there. There might be something real there, even if we can't see it.
That's what you meant? I thought I had this.
Yeah.
That's what I was
the
looking at.
one.
I knew I had it somewhere. So this is a
Yeah.
terrific book if you've not
Awesome book.
encountered Margaret Wheatley before.
Yeah.
Well, I thought that was a terrific observation, Cynthia, and it seemed a really profound way to sort of end it. Annika, I can't thank you enough for not just simply for the terrific presentation, but for helping us sort of bridge the science art divide, or the so-called two culture divide. And we knew that you'd be the exact person to do this. Annika appeared on my podcast in the very early days of the pandemic. I was just remembering the other day. We were doing this over Zoom. And just found her exploration of dark matter just absolutely fascinating. We had a wonderful conversation then, and I knew we had another wonderful conversation now. We'll get back to a couple other questions. I just want to say before we, because I know we're a little past the time we usually sign off. Hope you can join us next month, January 21st. We'll be back again. The theme next month is free. Which is what Columbus or Creative Mornings Columbus has always been, is free. So hope you're able to join us next month for this topic. Jesse asks, Annika, do you have any thoughts on the new James Webb Telescope? What the impact on your work specifically is going to be?
Yeah, so I did not have a successful first round proposal, also mostly because I didn't apply.
Oh.
But
hard to be successful then.
but my collaborators have been successful in getting observation time. You know, one thing that I think is interesting is there's currently a debate in our community as to whether this telescope should be renamed. So James Webb was a NASA administrator who helped push through big projects, but also drove out many queer scientists at NASA. And a lot of my collaborators or colleagues or acquaintances, notably Brian Nord, Chanda Prescott-Weinstein, Lucianne Walkowicz, Sarah Tuttle, and many others, have been advocating for a name change to reflect the possibility of science to be more inclusive, rather than putting a name of someone who is very exclusionary on this brand new facility. I think it's really important, you know, we're wrestling right now in the broader American context of how we name things, who we honor with, you know, monuments or building names and others. I mean, even at OSU, like last year in the University Senate, we were considering renaming buildings for people, you know, to take off the name of people who really have a problematic legacy. And so I think it's really important, you know, it's something that you maybe don't associate with science, of like, who do we honor and remember, and who do we name things for? But it's just as much an issue in our community as it is in any other community.
Rosalind Franklin.
Yeah. Millikan of the Millikan oil drop experiment, who, measured the charge of the electron, he was a eugenicist, like a big, like, enthusiastic, very problematic person. So Caltech, which had previously named, seemingly half of things on campus for Millikan because, of this amazing discovery, they're renaming buildings because they do not want to honor, it was really coming from a push by students and postdocs, sort of people with the least power in the community, saying, we just can't keep propagating these terrible legacies going forward.
We have time for more questions. You don't have to write them in the chat. You can just sort of speak them out if you want. We still have a few minutes. I know we're coming up on 10 o'clock here.
I just wanted to make a connection to what Annika said. There's a very similar problem in like the wellness and spiritual communities, where many like guru figures are incredibly problematic, like actively harming folks who are followers in many, many different ways. And then people still want to honor those ideas. And so I think it's just such a nuanced and interesting topic. So thank you for bringing that up, Annika. I had no idea about James Webb, so I feel much more educated.
Thoughts or reactions? I'm sorry, Jesse, go for it.
I just thinking about the connections to what we've already been talking about, in the process of science and learning and adding on new knowledge. And so that's, again, kind of one of these tensions we're struggling with of, can we acknowledge that people played a role in history, made meaningful contributions, and they also made mistakes and things were wrong, and we don't have to agree 100%. And how do we, what's the right way to maintain and remember what they did, both good and bad, because we have to learn from our history. We can't just erase and not acknowledge it. But then certainly thinking about, this telescope, for example, right? I mean, potentially if things go as planned, we're going to be talking about the James Webb telescope, like we talk about the Hubble, and it's going to just be kind of ubiquitous in language. Mm-hmm. Well, that may not be the name that we want to be, are there other ways to still, have his contributions in the history books or in the textbooks, but maybe not acknowledged in that way. So one other quick connection I just think is fascinating, thinking about how the work of this telescope is to bring the invisible visible, and thinking about how, Annika, as you mentioned, a lot of his work was kind of erasure of queer people, and how that's sort of like the opposite, as well as a lot of these kind of questions about, orientation and sexual orientation and whatnot, all of those connections of, well, I can't see this, or where does that come from, but these are, my emotions and my humanity is real. So you have to acknowledge that. So anyway, just thinking about a lot of connections there.
Thank you, Jesse. And Annika, Jesse is another former speaker. And as of now, you've just joined that group. So you are part of our former speakers at Creative Mornings Columbus. Joining, at least on this call, Cynthia and Jesse and Brandy. I forget, of course, that Brandy is a former speaker as well. So Annika, thank you again. We knew this would be an insightful presentation, and it certainly proved to be. Hope everyone, whatever holiday you and your families celebrate, hope it is a joyous holiday season for everyone, and hope to see you next month. Where the theme will be free next month.
All right. Okay.
Bye, everyone.
Thank you.